So the lectures before coffee were setting the scene about what we do, and then this lecture is primarily about what we've recently done in looking at thermally activated delayed fluorescence, and particularly the role of molecular vibrations. So I've already put up this slide. We have a schematic for TADF. We have a singlet state, a triplet state, the vibrational energy levels, and then if we consider that the fluorescence rate is a lot smaller than the reverse intersystem crossing rate, then we can write this as a thermal equilibrium. And then this tells us that all we have to do is make molecules that have a small energy gap between them. And so molecular design in that regime is incredibly simple. We could then, and actually more importantly, this tells us that the rate of reverse intersystem crossing doesn't matter at all for TADF. This is clearly not true. And there are many other factors that play a role, and one of those is the vibrational degrees of freedom. So one of the things that got us interested in this is this paper, which I've now forgotten to put the reference on. So it's a Journal of Phys Chem C. The first author is Chen. I think it's from 2015. And what they did was calculated the rates of intersystem or reverse intersystem crossing for various molecules. And one of the things that they showed is that considering the effect of the vibrational degrees of freedom and the spin-orbit coupling between the states involved, or the S1 and the T1, the rates that were extracted or calculated were a long, long way away from the rates reported experimentally. So you've got 4 orders of magnitude or 7 orders of magnitude. Now, we all know that experimentalists can make big mistakes, but 4 and 7 orders of magnitude is maybe a bit too much. So there's clearly something else going on. And now that I've annoyed Andy, I'll make him a bit happier by putting up one of his papers. So the other thing is that this paper from Jonathan, 2016, in which if you consider the equilibrium configuration of TADF, then you want, once you've got a molecule that is efficient at TADF, you want to make it as rigid as possible to stop non-radiative decays. And so here had these the donor acceptor and donor acceptor donor versions, put bulky side groups on this, stop rotation, the motion or the torsional angle between the donor and acceptor groups, and you'll reduce non-radiative decay, and you'll have the perfect molecule. Unfortunately, in this case, you switch from TADF to room temperature phosphorescence. So you completely turn off your TADF mechanism by adding the bulky groups. And so we wanted to have a look at this, and so we started by looking at the donor-acceptor molecule. Why did we look at the donor-acceptor molecule? Because the performance of these two molecules is very similar, and the donor-acceptor is smaller, so it's easier for us to calculate. And so what we then did was set up exactly as I've described, model Hamiltonian. We run quantum dynamics on it and try and understand what's going on. Okay. So setting up the model Hamiltonian, the electronic structure was TDDFT. And this is a potential. This is along one of the degrees of freedom. This is the 11th normal mode. The lowest red line is a locally excited triplet state on the donor. So you have a pi star excitation on the donor. The blue line is the triplet charge transfer state, and the black line is the singlet charge transfer state. And this is just one example. By calculating various degrees of freedom, we found that there were 3 degrees of freedom which were particularly important. And when I say important, I say that they exhibited significant non-adiabatic coupling between the 2 triplet states. Okay? So we have 3 states in this model. Non-adiabatic coupling is only active between states of the same multiplicity. And so these 2 modes were coupled, these 2 states were coupled by 3 particular modes. And they all had characteristics of donor acceptor torsions. So the motion was dominated by this torsional angle change. The Hamiltonian in matrix format here, but essentially we have 3 states. The locally excited state and the charge transfer state are coupled by spin-orbit coupling. This is relatively weak, 2 centimeters to the -1. Had a hyperfine interaction between the 2 charge transfer states because spin-orbit is formally forbidden, although this doesn't have, this has a very negligible effect. And then there's vibronic coupling, which is about this strength, but it depends on the amount of torsion of this degree of freedom. So we can take this model, and we can now run quantum dynamics on it. We can start in the T1 state, or the S1 state, and we can study either the intersystem or the reverse intersystem crossing process. Okay, so this is the dynamic, the population kinetics that comes out. So on the top here, we have the intersystem crossing dynamics. So we start in the S1 state. And in the bottom, the reverse intersystem crossing dynamics, where we're starting in the T1 state. And because we're starting in low energy state, this has an initial temperature of 300 Kelvin. The black line, in both cases, is the model Hamiltonian as I've just represented, where you've got 3 states, they're all coupled, the 2 triplet states are coupled by this non-adiabatic coupling. The green line, again in both cases, is where we've taken out this hyperfine interaction. Right? And you see it has essentially no effect on the dynamics within the first nanosecond or half nanosecond. This blue line here, the dark blue line, is the dynamics when we switch off the non-adiabatic coupling between the 2 triplet states. So we're looking at, in this case, we're looking at how we go from this lowest triplet state T1 to the S1 state. But by turning off coupling between 2 triplet states, we essentially completely kill the reverse intersystem crossing and the intersystem crossing dynamics. The red line is if we increase this non-adiabatic coupling by 10%. As I said, the beauty of once you've got a model, you can do what you want to it. And so this gives you an idea of how much effect the non-adiabatic coupling has. And then this light blue line is what happens if you half the energy gap between the 2 states. Okay, this is not particularly surprising in the sense that the closer the smaller the energy gaps, the more effective these couplings will be, and so the faster the dynamics. But the important thing in this respect is that if we turn off non-adiabatic coupling, then we essentially completely quench the crossing between the singlets and the triplet manifold. So what is the mechanism? Well, clearly, coupling between these 2 states affecting this transition not, you're not going to be able to describe this in first order perturbation theory, where you have some initial state, their internet action, and going to some final state. And so here you have to go to second order, where you have some initial state, which via some interaction goes to some intermediate state, and then this intermediate state, via another interaction, decays into this final state. And so what's actually happening is that the strong non-adiabatic coupling between these two states is promoting very quickly an equilibrium or a transition from this state, from the lowest triplet state, to the charge transfer triplet state. Okay. And this population transfer occurs on the picosecond timescale. So it occurs much faster than the reverse intersystem crossing because it's a spin-allowed transition, and the coupling is much stronger than any other coupling in the Hamiltonian. And then once you're in this state, once you're in the triplet charge transfer state, you can then have a second order pathway in which you couple, the matrix element is triplet charge transfer state with the vibronic coupling to this locally excited state, and the spin orbit coupling to this charge transfer state. And so if you want, you can think of it as step one and then step two. And the reason that this second order pathway is efficient is that you're taking advantage of the regions where the largest coupling is, but now, because these two states are almost degenerate, you've got good Frank-Condon overlaps. So the overlap of the vibrational wave functions in the initial and the final state is a lot better than in this case. Okay? So that enhances the rate significantly. So we've got this mixture of a first and second order pathway. We can also consider how this would change with the environment, because now we've got, and initially if we're considering two steps, say between two charge transfer states, it doesn't matter what your environment is, because, okay, the charge transfer state has a strong dipole, you change the dielectric constant of the medium, and that's going to stabilize or destabilize the charge transfer states. But the triplet and the singlet are going to be, to a large extent, affected in the same way. And so the effect of the environment is going to be a lot less. However, once you have this locally excited state, this pi star, this is not going to be influenced by the environment. So you now, having these three states, you have three regimes of TADF, where the first regime, you could have the charge transfer states are higher in energy than the locally excited state. You increase the polarity of the medium and shifts the charge transfer states down. Actually, this figure is a bit misleading because it looks like you shift the locally excited state up. But you stabilize the charge transfer states to an extent where they're all degenerate. I said the smaller the energy gap, the most efficient, that's when things are going to be most efficient. So this is the optimum case. And then you continue to increase the polarity of the environment, and you then reach the case where the charge transfer states are below. The effect of this, so this is an experiment by Mark in Andy's group, in which they put the donor-acceptor-donor version of the molecule into polyethylene oxide and cooled it down. As you cool it down, you change the polarity. And so you can see here the shift in the onset of the charge transfer band as a function of temperature. So you have the three regimes. Initially, the charge transfer state is higher than this locally excited state, and then about 200 Kelvin, they're degenerate, and then they drop below to 300 Kelvin, where there's quite a big gap. The black line is the emission intensity as a function of temperature. And on the right-hand side, we've taken the model and input. In here, we have experimental data as input, the energetics of the states as a function of temperature. And we can see here where here we plot the normalized intensity of the reverse intersystem crossing process as temperature, and we get a good correspondence between the experiment and the theory, showing that the mechanism is at least consistent.
So why the reverse intersystem cross rates decrease when temperature goes beyond like 200?
Because okay, as the temperature goes higher, although you'd expect more to be thermally activated, the energy, the charge transfer states are a long way below this locally excited state. And so you need, the coupling is less efficient, and so the reverse intersystem crossing is less efficient because that gap is much larger. So you do need, this vibronic coupling, but you still need the energy levels to be relatively close. It doesn't mean you can have them EV apart. So that's one of the other thing that's maybe intriguing is that the donor-acceptor-donor molecules and the donor-acceptor molecules behave in a fairly similar way. The efficiencies that they give out are certainly comparative, and this is a rather phenomenological, it's rather approximate, it's first order of why this is, but by adding, we can try and rationalize this with molecular symmetry, because these couplings have to be symmetry allowed or not. In the donor-acceptor case, we have these three states, locally excited on the donor, the two charge transfers. They have CS symmetry, A prime, A double prime, and we get this initial coupling and then this second order pathway. If we now move to the donor-acceptor-donor molecule, symmetry is slightly different, it's C2V. And now all that happens is we now have two locally excited triplet states. We have two charge transfer states, one from this donor to the acceptor, from this donor to the acceptor, and then double also the singlet charge transfers. We have exactly the same pathways, but because of the symmetry of the states, B1 in this case and B1 in this, you don't get interference between these two pathways. Okay? So in essence, you've doubled the number of pathways, but they're acting separately. Okay? This is, okay, do stress that this is a rather crude way of describing it, but at least it should give you an indication that on a molecular level, you should not expect automatically donor-acceptor donors to be better than donor-acceptors. Okay, so if you have a donor-acceptor molecule that works well, just by adding more donor or more acceptor groups, you're not necessarily going to improve performance. Now, it might be the case that by adding an additional group, you get steric interactions between the two of the groups, and that changes the electronic structure, and you get better performance. Then that's perfectly reasonable. All I'm saying in this case is it shouldn't be assumed that just by adding more groups, you're necessarily going to improve the performance of the molecule. Yep.
In your model, so where does it show which of the triplet state is charge transition, which one is local excitation,
Yeah, so it's only splitting that matters, yeah, yeah. Yeah?
How would this feature look like if they are not perfectly symmetric? So in reality, if there was something like this, it's not symmetric, so it's much or
so as soon as you add an environment or you have some temperature that makes things oscillate, then the symmetry is broken. Generally, so this would be at first order. To incorporate those effects, you could add higher order terms. Generally, first order coupling terms are the strongest. So for sure, as you add these additional terms, then it will blur the picture somewhat. I'm certainly not saying that this is a hard and fast rule. Just that you shouldn't automatically assume that it's going to, by adding more donor or acceptor groups, it's going to necessarily improve performance. There might actually, there might also be a very good reason in an actual device why the donor-acceptor donor works better, but at a molecular level, it shouldn't automatically be assumed. How should we think about this mechanism? Well, there's two kind of interchangeable ways of thinking about it. I talked about in terms of starting from some initially excited pi star state, coupling and population transfer to a triplet charge transfer, and then this second order pathway. In reality, also, as soon as we have coupling, the lines between these states become blurred. We don't have individual states. We have vibronically coupled levels. And the stronger the coupling, the harder it is to actually differentiate these. In addition, if we have a system that has many excited states in this region, which is perfectly possible, that are closer in energy and vibronically coupled, then we start to approach more of a band rather than these individual states. So these two are essentially interchangeable. It depends on the strength of the coupling. If you have very weak coupling, then you could view of these as completely independent. But the higher the density of states and the stronger the coupling, we'll be merging more into essentially saying we've got a manifold of triplet states. It's exactly the same if you're looking at an iridium complex with spin-orbit coupling. Spin-orbit coupling is very strong, and so it then no longer makes sense to talk about singlet and triplet states because they're so heavily mixed that you just have a manifold of states. Exactly the same here. As soon as you have vibronic coupling, you have a manifold of states. This is slightly different mechanism to the one that Crystal proposed and we'll discuss next. Essentially, but the most important thing is that the overall message in both cases is the same, that you've got to worry about the mixing between excited states. And the mixing is promoted by vibrational degrees of freedom. And so the vibrations are important. So, extended picture or schematic of TADF. We now consider this second triplet state, and we have the reverse internal conversion. So now we have not only one energy gap to consider, but there are two energy gaps. This is not limited to 3 states. The simulations I've done happen to be for a molecule that have 3 important states. There's no reason why you couldn't have 3 singlet states very close together and 6 triplet states close together. And then you have 9 states all mixed and contributing. In some ways, that would probably be more efficient because, again, you've got a higher density of states. Coupling is more effective. So there's nothing limiting this. I'm not saying there's anything magic about 3 excited states at all. So just in terms of the relative strength of, or the effect of non-adiabatic coupling, so this is 2 curves for the rate of reverse intersystem crossing normalized to what the initial parameters of our Hamiltonian. And this is for 2 different energy gaps. So this is a slightly smaller energy gap. What happens to the rate as we increase the non-adiabatic coupling? So if we manage to increase the non-adiabatic coupling by a factor of 3, we can in principle achieve a factor of 4 in the rate of reverse intersystem crossing. This actually depends somewhat on the energy gap as well. But again, this non-adiabatic coupling is promoted by the vibrational degrees of freedom. And so this is something that to consider. The other thing, as I said, we have we now have 2 energy gaps, not just one. We have to consider the energy gap between the S1 and the T1 state, and also the T1 and the T2 state. And so this plot here at the top, figure A, shows the rate of reverse intersystem crossing as a function of these 2 energy gaps. And this is 2 cuts from this plot. Okay? This black area is left out because it would correspond to the T2 state, the charge transfer state, being higher in energy than the singlet state. The triplet state of the same character cannot be above the singlet state. So here, this plot, figure B, shows the rate of reverse intersystem crossing as a function of the energy gap between the S1 and the T1 state for a fixed T1, T2 energy gap. And as perfectly expected from TADF, you see this exponential decay, which is just from the fact that as the energy gap gets bigger, it's harder to thermally activate from the T1 to the S1. Now, if we take a fixed S1, T1 energy gap, and then see the rate as a function of the T2, T1 energy gap, then as this T1, T2 energy gap increases, so the rate of reverse intersystem crossing increases. So what this is telling you is that it's important to keep this S1 and T2 energy gap still small. There is less importance on the T1, T2 energy gap. And the reason for that is because the non-adiabatic coupling is so much stronger than any other coupling in your system, and so it's less sensitive. It can still operate at a larger energy gap. Right? So as I said, with the 3-state mechanism, the S1 and the T2, the reason the second order coupling is so effective is because of the good Frank-Condon overlaps. If you increase this energy gap too much, then the Frank-Condon overlaps become poorer. So with this in mind, what we were interested in is the fact that if you want to characterize your TADF molecule, you might look at the onset of the fluorescence and the phosphorescence band and extract some gap between the 2 states. And you might also then do an Arrhenius plot to measure the activation energy for TADF. And what was seen in quite a number of cases is that for the higher performing molecules, these 2 energy gaps differed quite significantly, sometimes by up to 0.4 eV. So we wanted to identify the role of non-adiabatic coupling in this. And so again, we have this three-state model, have the non-adiabatic coupling, and we did an Arrhenius plot, so the rate of the natural log of the rate of the reverse intercrossing, 10 to the 3 divided by temperature, for two cases. The first one, the S1T1 energy gap was 0.1 eV. The second case was 0.06 eV. But in both cases, the energy that we get out from this Arrhenius plot, the activation energy, is significantly less than this energy gap, which would suggest that this non-adiabatic coupling offers an ability to achieve activation, reduce the activation energy for TADF. And so, in another way of saying it, it means that you can get away with molecules with a larger energy gap, and if they've got a larger energy gap, probably means the HOMO-LUMO overlap is larger, and so your fluorescence rate is larger. Okay? So you're still getting TADF, but you're also getting the combination of TADF with a good radiative rate. The reason for this, the reason that this occurs, is that as soon as you add non-adiabatic coupling, as I said with the band picture, you can no longer think about these two states as pure individual levels. And this is actually showing the population of the triplet charge transfer, so this T2 state, as a function of temperature. And at 300 Kelvin, you've got about 27% of your wave packet is in the triplet charge transfer state once these two states have equilibrated. But at 0 Kelvin, you've still got 20% in there. And this is because of the strength of the non-adiabatic coupling. So in fact, only 7% is thermally activated. So here, a significant portion of the wave function is actually seeing this energy gap, which was 0.03 eV, rather than this S1T1 energy gap. Okay. Now, I have to stress that this is not the only dynamics that will affect this, because if you've got a T1 state, which is a different character to the S1 state, the probability is that these potentials are not going to be parallel. And so the energy gap at their minima, the optical gap, may be one thing, but as they're able to oscillate, you're also able to maybe reach a region on the potential where the energy gap is smaller than at their minimum geometry. Okay? So TADF is more likely is going to happen there as opposed to where the gap is larger. So, and this is in one of I forget the reference. It's one of Adachi's papers. But essentially, this is highlighting that although it's not the only mechanism, the non-adiabatic coupling will have the potential to give you an effective energy gap smaller than your energy gap it is in reality. Okay, given the interest of time, I'm probably going to skip this. This is how you always have to consider the regio and the stereo selectivity. But so using that information, how should we consider design? Because, okay, I tell you that non-adiabatic coupling between the T2 state and the T1 state is incredibly important. And so if you get strong non-adiabatic coupling, you can reduce the effective energy gap. But I've also told you that the energy gap between these two states the S1 and the T2 in this three-state model, is critically important. So you'll still want to get a small energy gap between these two states, which are of the same character. And so to achieve that, you're still reducing the HOMO-LUMO overlap. So what I think is a better way of achieving TADF is to make sure that you have a triplet state that is aligned with your emissive singlet state, but those two states should not be of the same character. And then then you have more freedom with the corresponding triplet of this singlet state, which has to be below the singlet. And if you've got more freedom to choose a larger energy gap, or to synthesize a larger energy gap, then you can achieve a larger radiative rate because you're not so reliant on such a strong charge transfer to minimize this energy gap, because you've already got the small energy gap here. So in this case, in these two models, you would get, if the energy levels were exactly the same, and there's no reason why the non-adiabatic coupling would be any different, you could achieve better TADF because, in this case, this state is going to be less charge transfer, and so it's likely to have a larger radiative rate. Okay? At the end, don't ask me to propose molecules that achieve this. I'm merely putting this forward as a mechanism. Proposing molecules is the next stage. So, just really to summarize what I've been trying to tell you in terms of considerations for TADF OLEDs, certainly at a molecular level, is there are various levels of theory that we can do. Some of them are quite coarse-grained, but the advantage of that is that we can calculate an awful lot of molecules, as demonstrated by Alanis Buruguzic's approach, in which they were able to calculate 1.6 million molecules in a very short amount of time. And this is great for potentially proposing new architectures. Okay? Moving from phenothiazine or carbazoles to something that's maybe completely different, that's not been thought of by to date. We then have to consider the role of molecular structure, the isomers, what difference that makes. We also have to consider, I hope I've convinced you, the role of molecular vibrations. But the other thing, so these molecular vibrations, they contribute to the reverse intersystem crossing, so the TADF. But they're also going to contribute to the non-radiative decay. And let's hope that the molecules that promote reverse intersystem crossing are not the ones that promote non-radiative decay. And so this is kind of an active area that should be pursued. Obviously, we have to consider the energy gaps, but we maybe have to consider more than just one energy gap. And as soon as you start introducing states that have different character, then you have to start considering the effect of the embedding environment. And not only just the static shift that a higher polarity environment would include, but also the dynamics of this. If you have a very charged transfer state and it lives there on the long nanosecond timescales, you have the ability for the surrounding host molecules to align to some degree to that dipole. Now, this may be a very minor effect, but shifting your energy levels by 0.02, 0.03 eV, that's already KT at 300 Kelvin. So this could have a significant effect on the performance. So I think the important thing is that we really need to marry all of these approaches to if we're going to achieve these high performance TADF OLEDs. So I said, I hope in just over 2.5 hours I've managed to give you some insight into theory, potentially more importantly, the approximations that come with it, the limitations. And so next time you pick up a theory paper on TADF, you'll be able to critically assess what's been done, how we can use theory. The one thing I haven't really discussed is the quantum chemistry and the actual calculation of spin-orbit coupling, which is next. How we can use quantum dynamics, the MCTDH method, developing the model of potential energy surfaces, and then what actually needs to be done to characterize the role of molecular vibrations, the effect of non-adiabatic coupling, and these new proposals for direction of designing organic TADFs. And yeah, with that, I think my time is up.